Thanks everyone for being here. My name is Arnaud. I'm a software engineer on the RabbitMQ team at VMware. And in this talk, I will cover a new feature that we introduced in RabbitMQ 3.9, streams. Streams are a new type of data structure in RabbitMQ. They model an append-only log. We'll see more about the details of what exactly an append-only log is. Streams are persistent and replicated by default, and they are basically always persistent and replicated, which is not always the case with queues in RabbitMQ. They have also quite a big difference with traditional queues. They have non-destructive consumer semantics. This basically means that when you read consume messages from streams, you don't remove them. Whereas with queues, you actually read and remove messages from the queue. So this is one of the biggest differences compared to queues, and really basically the non-destructive consumer semantics. You can access streams through the traditional AMQP 091 protocol, which is one of the most used protocol in RabbitMQ. And they are also accessible through the other protocols that RabbitMQ supports, MQTT and Stomp. But we also created a new protocol just for the occasion, just for streams, that we call the stream protocol. Streams shine for some use cases. They have strong points. They are good for large fanouts. So when you have applications in your system that need to read the same messages, this is a fanout. And streams are good for that thanks to their non-destructive consuming semantics. So you can have applications reading the same messages from the same stream without competing. They have also replay and time traveling capabilities, so you can attach to some point at some point in the stream to consume, and you can consume your messages, and the same application can go back, attach to the same point or before, after, and replay again the messages and redo some processing. They are also good for high throughput scenarios, so they are much faster thanks to this new stream protocol than traditional queues. So if you want high throughput, a lot of messages per second, they are quite good for that. And they're also good for large logs. Messages in streams are always persisted on the file system, and the messages don't stay in memory. They just happen to be in memory when you publish messages to them and when they go through from the file system to consumers, but that's all. They don't stay in memory for long. So why do we need streams in RabbitMQ? Why did we introduce streams? Traditional queues have limitations. We cannot do everything with them. They are very flexible, versatile, but they are not good fit. They are not a good fit for some use cases. So streams are there to complement queues, to expand the use cases that we have with RabbitMQ. So with stream, we basically unlock new use cases that could have been tedious or difficult, even impossible to achieve with traditional queues. So let's see how traditional queues work in RabbitMQ, and to get even more the differences between queues and streams. So this is the typical state for a queue, and in RabbitMQ you have a queue with a couple of messages and a consuming application. So when you register the consumer, the broker will start dispatching messages. So you have first messages, the first message going from from the queue to the consumer, and the consuming application can start processing it. When at this point, the message is basically at 2 points. It's on the server side and also on the consuming side. The broker still needs to care about this message because it can be rejected. It must know that it hasn't been acknowledged yet. So when the application is done, it can acknowledge the message, and this is at this time that the broker will actually get rid of the message and consider it just processed. So this is what we can call a destructive consuming, and this is what we have with queues. So when you read from queues, this is not a read-only operation, actually. You read and remove. So with streams, it's different. You just read and you don't remove messages. And the fan out, so how does it work with queues? So you have a message coming in, they go from an exchange and they are routed to a queue, and then you have a consuming application. So if you want another application to process the same messages in a different way, you need to create a new queue, bind the queue to the exchange, and start consuming with your application. And if you need a third application to process the same messages, same thing, yet another queue, a new binding, and a new your new application. So it's fine, it works pretty well, and it's been there for years, but it doesn't really scale when you want many applications. It can be a bit a waste of resources if you need to create more and more queues. So with streams, we have a better way to handle these kind of scenarios than with queues. So as I said at the beginning, streams model a log, an append-only log. So what is it exactly? So it's a FIFO data structure. You basically accumulate messages in your stream. The oldest messages are at the beginning, and the most recent messages are accumulated at the end. So the stream is kind of immutable. It's not really immutable because you can add messages, but when a message is entered the stream, when it's there, it cannot be removed. And this makes the log abstraction, the stream, quite a simple data structure compared to queues when messages are always removed, added and removed. So we have also quite an important concept here, the offset. So it's mainly technical, but this is a concept that we cannot avoid when we deal with streams. So the offset is just some kind of technical index of a message inside the stream. So it's like the index in an array, to make it simple. It's not a business concept. It's not like the unique message ID. It's really just technical. Okay, consuming in streams. So when we have a stream and messages in it, we can attach a consumer pretty much anywhere. So here we have an example of a consumer which attaches at the beginning of the stream. So it's going to start reading the first message, and then we'll move along to all the messages in the stream. You can also attach at the end. So there are actually two flavors into when you attach at the end. You can just attach at the almost the end. It means that you will get a last batch of messages, and then new messages accumulating into the stream. You can also attach at the very end. So you will get new messages only when they arrive, when they enter the stream. So just a couple of what we call different offset specification for the end of the stream. And you can attach anywhere. So the consuming application can specify an offset. So this index that I mentioned before, but this is a technical index, so we have also something more meaningful, and we can attach also using a timestamp. So it means that if you want to consume messages from today at noon, it's possible. You can attach your consumer at this point. And we can have any number of consumers on a stream, so they can work all together and they read the same messages, and they don't compete with each other. So one consuming application will not steal messages from the other applications. They just read the same thing depending on where they start. And the same application can read and reread the stream several times. So you can have your application starting consuming at the beginning, process and do some computation with all the messages. And the next day, you can start again at the beginning and do the same processing with just the additional messages that we accumulated during the day. This is an example of the topology of a stream inside a cluster of 3 nodes. So streams are persistent and replicated. This is how they are actually, and there's no really an option for this. With queues, we can have them in memory. They can be persisted or not. They can be only on one node, but streams are just persistent and replicated. It's quite consistent with their semantics. So when we have a stream, it's going to have a leader which will be located on one node, and followers, replicas, on other nodes. So the replicas will just basically follow the leader and synchronize, replicate data. The leader is usually the one, is the only one that can handle write operations, so accumulating, publishing messages. And the replicas will typically be used to consume messages. So if you have well-behaved client application, they should basically work this way. Publishers should connect to the node where the stream is located. And this will make the writing more optimized. You can actually connect to any node, but the leader must handle actually the writing. So if you don't connect to the leader, you will just have an extra network hop. And for the consuming side, you will typically connect your client application to the nodes which host replicas. It's just to offload the leader. The leader can actually dispatch messages to consumers, but we can imagine that it's going to be busy writing, dealing with the writes. So it's better to offload the leader and plug applications, consuming applications, to the nodes with replicas on them. And we also have to know that there's no one leader node for all the streams. They are actually spread. They are just a bunch of small clusters in the way. So in this example, we have stream number 1, which is at the top, and the leader is on the first node, and it has 2 replicas on 2 other nodes. And then we have stream 2. The leader is on the second node, and then it has 2 replicas on node 1 and node 3, and stream 3 as its leader on the last node, and the 2 replicas on the 2 first nodes. So this is what we call the leader strategy, the leader location strategy. And the default one we have is called list leaders. So basically the broker will try to put the leader of a newly created stream on the node with list leaders. Okay, so now about the client interaction with streams. So streams can be accessed with the AMQP 091 protocol. So for example, here we have a sample with the Java client, the AMQP Java client. So if you want to declare a stream, it is the usual qdeclare AMQP function. You just need to specify the type with the xq type parameter here. So with the value stream. So it's the same thing as with Chrome queues, except that we use a stream in this case. And when you want to consume, same thing, you can still use AMQP. So this is again the common basic consume AMQP function. You specify the stream you want to consume from. You always need to acknowledge where auto acknowledgement does not work. And you can specify where you want to start consuming from using the xstream offset parameter. So here, this is at the beginning. And then this is the same thing as usual. You provide a callback for incoming messages. So this is quite a nice model because we have this new feature and we can use it with the same client libraries. It's just we have to know about the semantics, which are quite different from traditional queues. About publishing, there's no sample for publishing with AMQP because it's the same as usual. You publish to an exchange. So this is how streams fit into the existing AMQP model. They are just a new type of resource. They are a queue, but with some specific semantics. So you can create a stream, bind it to an exchange, and then messages routed to this stream will just be added to this stream. There's nothing different from any other queue types, actually, in this case. So a bit about performance. So here we ran some tests on a 3-node cluster on GCP with some reasonable VMs. And we get a better throughput, higher throughput with streams. So with a Chrome queue, which is also replicated, a persistent and replicated data structure, we get about 40,000 messages per second. And with a stream, we have 64,000 messages per second. So it's about 50% faster. And it makes sense, it's quite consistent. Streams are actually a simpler data structure than Chrome queues. They don't have to deal with complicated things like message and acknowledgement, rejected messages, requeuing, and all that stuff. So they are just simpler and they are a bit faster. So this does not mean that you need to throw away your Chrome queues because streams are faster. They are just different. Chrome queues are still our state-of-the-art replicated and persistent queue, and streams are for other use cases. Okay, but this is all on top of AMQP, so for Chrome queues and for streams. And we mentioned this this stream protocol that we created for the occasion. So the numbers are quite different when we use the exact same configuration, the exact same size for message. But if we use the stream protocol. So we were at about a few dozens of thousands of messages per second with AMQP, and we get over 1 million messages per second with the stream protocol. This is actually explained by several things. The stream protocol has been designed with performance in mind. It uses a lot of techniques like batching, send file to be much faster than AMQP. It's a bit also simpler. And it can actually exploit all the optimization in the storage that we've been doing for streams. So let's explore this new protocol. So it's fast, much faster than AMQP. It's been designed for that partially. It's available through a new plugin in the core distribution. So in RabbitMQ 3.9, there's a new stream plugin that will start a listener on a new port. And this is where new clients can connect using the stream protocol. And it's fully integrated with the existing infrastructure that we have in RabbitMQ. So the management UI, the REST API, Prometheus, the streams have their own metrics and so on. So they are very really a first-class citizen inside the RabbitMQ ecosystem. About the tooling, so we have a dedicated stream Java client using this this new stream protocol. We can call this Java client the reference implementation of the stream protocol. We have also a Go client which works. It's more considered a work in progress compared to the Java client, but it's working. And we have also performance tools on top of these two clients. So it's basically all usable. You can grab the client or grab the performance tool and experiment with streams on your own systems. So the stream protocol is a bit simpler than the AMQP. There's no routing with the stream protocol. You just publish to a stream. There's no exchange involved, and you consume from a stream, just like from a queue. So again, this is where we can find out why actually the stream protocol is faster. There's no routing, there's no logic which needs to go inside messages to decide where the message should be routed. Basically, when you publish a message from your client applications, it goes to the network, through the network, and then to the plugin, and almost directly to the storage. Okay, so that's why publishing is, for example, much faster. We still have some good interoperability between streams and the rest of RabbitMQ. So you can, for example, have a stream client application at the bottom, publishing messages to a stream using the stream protocol. And these messages can be consumed from an AMQP 091 client application. And it works also the other way around. If you the AMQP client publishes messages, the stream client can read them. So it means that we have conversion rules inside streams for over protocol. It will all work it all works consistently between protocol, and depending on the direction of the conversion, you don't lose any data from your messages. So this is how you could imagine using streams. So imagine that this is what you have in your RabbitMQ 3.8 cluster. You have a publisher publishing messages to an exchange. Depending on the routing key of your messages, they get routed to different queues. So you have a queue for each region in the world. So you have a queue for Americas, you have a queue for Europe, you have a queue for Asia. And for each queue, you have a dedicated consuming application that will do some specific processing for the region. So if you upgrade to RabbitMQ 3.9, you can just create a stream, bind it to the exchange with a wildcard so that all messages are still routed to the queues, but the stream gets all the messages. And then you can plug an application using the stream protocol on this stream. And we can imagine that this application will do some worldwide analytics every day, reading and rereading the stream very, very quickly. So this is how we imagine streams can fit into existing applications. This is really an addition that you can use or not with RabbitMQ. More about performance. So these are just results to give us an idea of the performance. So these runs are a bit artificial because we use some very small messages. The messages here are 12 bytes. This is a bit ridiculous for, I mean, it's not real, but it gives us an idea of the cost of processing one message. And then it's also help us to compare with AMQP, for example. So the interesting part here is that with on this configuration on a 3-node cluster with in VMs, we get about 1 million messages per second on one stream, and we scale almost linearly with 5 streams. We reach almost 5 million messages per second. So after some profiling, we know that sometimes the disk can be a bottleneck. At least they introduce some latency when they actually write data to they persist data. So this can explain that it doesn't scale exactly linearly, but this is quite encouraging results. For the data rates, they are also quite good. They scale also almost linearly. So remember, we were at about a few dozens of thousand messages per second with one queue using AMQP, even with a stream using AMQP. So here it's over 1 million, so it's 25 times faster. There's TLS also, TLS support between client applications and the server. So we see that here the TLS introduces a bit of overhead, but it's not that bad. It's just a few percent. So we are still over the million messages per second threshold. So it's not that bad. We actually thought that TLS would introduce more overhead, but it's quite good. And we have also a specific mode which is optimized for throughput. We call that the sub-entry batching mode. So just imagine that we are already batching a lot, and with this mode, we actually put batches into batches. So for the same cost of dealing with one message, we actually handle several messages. So here we get even more higher throughput. So it's about 4 million messages per second on one stream, and about 17 million messages per second for 5 streams. It also helps to get a better data rates. So here we reach several hundreds of megabytes per second for even with small messages, which is quite good. So even with more streams, we reach about even more than 20 million messages per second in some benchmarks. So this is typically the option that you could use if you want a very high throughput in your system. So as I said previously, that streams are integrated with pretty much everything in RabbitMQ. So there's also a new stream management plugin in RabbitMQ 3.9. It will create a new tab, a stream tab, where you can list the stream connections. So connections using the stream protocol. It's very similar to the existing connection page. It's just that stream connections have some different columns, but it's pretty much the same layout. And then you can click on the connection to learn about the details. So again, it's quite similar to the traditional connection detail page. It's just that here streams stream connections have some small differences between AMQP connections. So for example, publishers are entities in the stream protocol. So here in the middle, we see that we have for this connection a publisher which publishes to stream-5. Okay, so about the guarantees that we have in streams. So we have at least one guarantees. It means no message loss. There's a publish confirm mechanism which works the same as the AMQP publish confirm mechanism. So it consists in getting an asynchronous acknowledgement once the message has been persisted and replicated, has been taken into account by the broker. There's also a deduplication mechanism. So it can actually, the broker can filter out duplicate messages based on the publishing sequence. So the publishing sequence will typically be like something like the line in a file, or the primary key for of the record in a database table. And if you have one message for each of these values of this sequence, you can actually make sure that messages are deduplicated if you send the same messages. This is something that we have only in the stream protocol because it's not built into AMQP. And we have also flow control. So on both sides, so fast publishers will be blocked. So if the broker cannot keep up with some very fast publishers, their TCP connection will be blocked. And on the other side, when the broker dispatches messages to consumer, consumers ask for new messages when they are ready. So this way, the broker will not send blindly messages to consumers that cannot keep up. Other features, so we can attach to a stream using an integer-based offset, but we can also use a timestamp. So we have two types of indexes. With streams, we don't remove messages when we read them. So in theory, streams can grow indefinitely. So there are retention policies. So when messages in a stream gets too old, or when a stream gets too big, they will be truncated automatically. So this is something that you can set up on the broker side, for example. There's also server-side offset tracking. So this is a consumer feature. When you have a consuming application getting new messages, it can store on the server side the offset of the last message it processed. So it means that this consuming application, if it stopped and it restarts later, it can retrieve the index of the last message it processed and restart where it left off. You can choose also to store your offsets somewhere else, but there's this feature on the server side. And we have also TLS for client-server communication. So this is a reasonable set of features for a first release. We'll have now a quick focus on the Stream Java client. It's not exactly to bore you with some Java code, but it's more to give you the possibilities of streams, and also what we have in mind for new client libraries. Basically, we would like to have more advanced libraries in the Rabbit ecosystem, not just libraries which are a mapping between a programming language and the protocol. We want our libraries to bring more value. So this is hopefully the case with the Stream Java client. So when you start your application, your client application, if you use the Java client, you will use this environment object. You will typically have one instance in your application, and this is basically some kind of context between your application and the cluster. With the environment, you have a couple of methods to manage streams. So you can create new streams, you can delete streams. And this is from this environment object that you can create publishers and consumers. Let's say that this environment object, which is really a client-side concept, is the layer between your client application and the cluster. So then from this environment, you can create a producer. So you have an API and you just need to specify the stream you want to publish to. It's quite simple. And then you have a message builder API. You can add a binary payload to your message and also headers, all that kind of stuff. We have a quite a sophisticated message format with an advanced type system. And then you send your message. So you send the message and you provide a callback for the publish confirm, which will be called asynchronously. So the API is very simple. Behind the scenes, the producer, the client does a lot of things for the developer actually. And the client tries to be smart. So you saw that you don't have to deal with connections. The client will actually look up the node where the leader for this stream is, and it will create a connection to this very node to basically enforce best practices. For a consumer, you have also a builder API. You specify your stream, where you want to start consuming from. So here from the beginning, and then the callback code for incoming messages. And that's pretty much it. So same thing here, the client will look up a node where there's a replica for this stream, and it will create a connection to this node to avoid loading the leader too much. So the Java client is also configuration based. So for example, it accumulates messages to send them in batches in a publishing frame from the stream protocol. And you don't have to deal with that. You can just specify the batch size and that's it. It will be handled under the covers by the client. Same thing for the consumer side. You have options like the tracking strategy. The client can store the offset automatically for you every 10,000 messages, for example. And the client will try to spread consumers across replicas, so creating new connections to the appropriate nodes. And connections can also be reused when you have streams which are on the same nodes for consumers. The client will try to reuse the same connections. So all this connection intelligence is actually managed by the client under the covers. We don't want developers to deal with that. Okay, so the state of all this, we have an RC out for just a couple of days. So this is 3.9 RC1, so you can experiment with it. All of this will ship in RabbitMQ 2.9, which is due in the next couple of weeks, basically this summer in July, hopefully. And you can start experimenting. So you have the binaries available, you have Docker images, performance tools. So we are just waiting for some feedback from the community before actually doing the GA. The roadmap. So this is what we have in mind, but it will also depend on the feedback from the community. We would like to have some partitioning mechanism. So it's basically to scale out. So we have this in mind to have some kind of logical big stream that we call internally so far super streams. And such a super stream is actually backed up by streams underneath, but we don't want this notion to leak into the model. Actually, we would like to stay to keep this actually just a concept. And we would like also to provide a way to scale out consuming. So it could be done with competing consumers. So basically, consumer will consume from the same stream, and here they will be competing actually, and the the stream will actually dispatch a set of messages in a round-robin fashion to different consumer instances. So this will basically scale out the processing of messages. So as a conclusion, streams are a new replicated and persistent type of structure in RabbitMQ. They model an append-only log. They are good for large fanouts. They provide replay and time traveling features, and they are good for high throughput scenarios, and also for large logs because they store their data on the file system and never in memory. So you're welcome to try this out. And I'm done. I guess we have time for some questions.
Thank you, Arnaud, for introducing us to these new features and streams. Yes, we do have a couple of questions. Some of these are actually already answered, but we'll ask them anyway for the benefit of the video. So, do streams and quorum queues sit nicely on the same cluster? Do they have different requirements with respect to cluster size, CPU cores, and RAM disks? That question was asked by Adam Casey.
They kind of need the same type of resources. They are both replicated and persistent data structures, so a fast disk will be good for them, basically. And they will indeed compete for the same resources because they are on the same cluster. So it will all depend on your use cases, but indeed they are this kind of hungry for the same type of resources.
Our next question is how does priority work with streams? This has been asked by Chinmay Patel.
So there's no priority support, just like with queues. They are just added one after the other. Messages are added in the stream one after the other in the order they are received. And then you read them in the same order. It's quite simple, and it's why it's so fast compared to queues.
Okay, I'm going to open this one out to Gilberto Garcia. Do you want to ask your question? Okay, so any advice when to use streams or just to go with the fan out strategy, given you don't need to consume all events when you plug a new consumer?
It's hard to say depending on the use case, because in both cases you cannot really filter out messages, but I mean just only on the client side. So in theory, for large fanouts, streams are maybe a better option because this is one of the typical use cases they are good for. They avoid to create new queues, bind them, and one stream is just cheaper than several queues. But again, it really depends on what you want to do. The nice thing is that with streams, you can attach wherever you want. So it can make sense, for example, in some use cases to be able to attach at some point in time. And you don't have all this, you don't have this freedom with fan out based on queues. And same thing, if you want to process a backlog of messages, you have a new application and that you want to benefit from this fan out, and it wants to process some existing messages. They are just not there. These messages are not there because the queue does not exist yet. Whereas with streams, they are just accumulated. The messages are already there.
Okay, we just got a quick follow-up. What can be considered a large fan out?
It really depends again, but we have people using dozens or hundreds of queues on the same exchanges. So this is when it gets a bit, perhaps even more in the wild. I don't know. Yeah, large fan-outs can be considered when you have more than dozens or hundreds of consuming applications, when you need the same number of queues for different use cases. So you can be even more queues.
Okay, open this out to Gerhard, who's making a comment.
Yeah, my favorite stream features is that it has minimal memory overhead, really, really small, and the messages don't enter the Erlang VM, which means minimal binaries. From the TCP socket straight to disk, send file magic. With TLS support, it's really, really nice. So that's how we can basically get a lot of messages through Rabbit without actually using any memory. It's all the kernel handling all of it. And this also applies when we replicate the messages, which is a big deal. It doesn't enter the Erlang distribution. It doesn't enter the Erlang point-to-point TCP connections. It's amazing.
Good stuff. Thank you.
Yeah, that's true. We use for dispatching messages, we use send file. So this is a system call, and it makes even more sense when actually I'm thinking about that now. With fan-outs based on queues, if you have slow consumers or consumers that just go offline for some time, the message will accumulate in the queue dedicated to these consumers, and it can end up eating a lot of memory, which is not the case with streams. The consumer can go all away, store its offset before, and then come back, and it will just read the messages from wherever it was before.
Okay, we have a question from Brandon. Do you want to ask your question? So the question is for client libraries as on C++, is there any development there?
So for now we have Java, and the Java client is quite advanced already. We cannot guarantee that it's production ready, but it's in a good state. We have also a Go client, and we would like also to implement a .NET client. C++ is not on the table right now for different reasons. I'm not sure it's what our customers would like first. People are asking for .NET, for example, and we indeed don't have really a lot of expertise in C++. And this is where actually we could get some help from the community. It's an open protocol. There's the definition on GitHub, and the protocol is quite simple to implement. Actually, it's just a binary protocol with some framing. If you want a sophisticated client, which is smart, what we are trying to do with the Java client, it can get more complicated, longer to develop, but it's still quite a simple protocol. So right now, for in the RabbitMQ team, we would like to develop Java, Golang, and .NET, which is what we have on the table.
I'd really like Gabriele to give his talk about stream client development. That's one talk that didn't make the cut. I'd really love to see that. He has some great ideas.
So yes, we are preparing some things. Now is internal. At some point we will publish a document or some things to help to write clients based on my experience. So all the mistake that I did when I was writing the Go client, so to avoid my same mistake. So at some point we will deliver the document and maybe some talk. But I agree that the protocol itself is very easy, and writing the smart client around maybe can be a bit complex, but if you know how to do that, let me say that it's not so complex as protocol.